understand, and that's more or less, if somebody was not in the previous lecture, this is just as good. So we have a Navier-Stokes equation, which, as far as we know, perfectly describes motion of a fluid, and it's written for incompressible fluid with a density 1. And we wanted to find a flow around a body, let's say a sphere, which moves with a velocity u. And we found out that it's a complicated partial differential nonlinear equation. So what we did, we understood that this term could be neglected if Reynolds number defined as u r divided by nu, where this nu is a diffusivity of momentum. If this is very large, then this term could be neglected. So we neglected it. Then we immediately realized that the remaining equation, which is ideal fluid equation, it conserves not only energy and momentum, but also a new type of invariant. It's non-local invariant called vorticity. And it's a circulation of a liquid contour. And because it conserves vorticity, if I started from rest and started moving my body, then vorticity was everywhere 0. And within this ideal fluid approximation, it would stay 0 all the time. Then I can use potential substitute. I can assume that my velocity is a gradient of phi. And it immediately turns this equation into Laplace equation, for which I find velocity. So it's Laplace phi equal to 0. And then you find pressure from the equation, which is this one. So it's a linear problem to find velocity. And then you find pressure from it. What we've realized that the force which acts on this body is such that it's integral of pressure over the surface of the body. But velocity, which we found, corresponds to, because phi must be linear with u and it depends on anything else, that this is just a dipole solution. And in this dipole solution, velocity is, of course, also a dipole solution. Velocity is behaves like 1 over r cube, but velocities has a symmetry left-right, namely v squared is the same here, it is the same here. So the pressure, this term gives you no contribution into the force, which means that only out of this term, time derivative, comes a contribution. And we find out that the force acting on a sphere was minus 2 pi over 3 rho ddt r cube u. So it was a time derivative of something which is like a displaced volume and a velocity. The moment it's a constant, namely we move with a constant speed and we don't change our shape, the force is 0. And that's a total disaster. By itself, this formula is beautiful. It's a first renormalization in physics. It shows you how you acquire mass. But if there would be no force, that all birds, all planes would immediately fall down, right? So there's just would be nothing to support it. And then so that was before previous episodes. So that's what we are doing today. Let's bring it back. There was something important that they were missing here. But the moment that we look at this whole equation, we realize that this is still a solution of this whole equation, right? Because if Laplace phi is 0, then Laplace of any gradient of phi is also 0. So this term is identically 0 if I plug there this solution. Is it true that we already have a solution for the whole Navier-Stokes equation? What do you think? Well, it's apparently true. It is a solution of the equation. But it does not satisfy what? Because you not only need to satisfy the equation, you need to satisfy a boundary condition. The boundary condition must be that at infinity you would have 0 velocity, but on the body, what was the boundary condition which this solution satisfied is that the normal component of the velocity of the fluid is equal to the normal component. So the fluid does not penetrate through the body, but it can slide. This equation is higher order, which means that it must have extra boundary condition. And this extra boundary condition depends on the type of a material of which it's made. If it's solid, you need to impose a no-slip condition. If it's a gas bubble, you need to impose no stress condition, requires that the viscous stresses are zero over there. But it's a boundary condition which this does not satisfy. So unfortunately, it's not a solution. And we are back to trying to find a solution. And now we'll go to the opposite limit. That's what usually physicists do. You cannot solve a problem, so you go to one limit, then you go to another limit, then somehow you match them in between, and you say that everything will live happily ever after. So let's consider Reynolds much less than unity, which essentially is the following statement, that if you move with the velocity u, you push a body, and then you stop pushing it, how fast it would stop? Well, the time it would take to stop is for its momentum to diffuse away, right? And the time to diffuse this would be r squared over nu, right? So if you multiply by u, that would be the distance which your body would continue moving after you stop pushing, which you can write as r times re. So the statement that Reynolds number is much less than unity means that any body stops on a distance much less than its size, which in other terms means that the momentum diffuses instantly, like everywhere, okay? And now we can neglect this term, and it's a stationary solution, so we can neglect this term, by the way. So what we get so-called Stokes solution, nu Laplace v equal to gradient of pressure. Again, like most 19th century people were solving Laplace equation equal to 0, you can always turn almost any equation of fluid mechanics, at least stationary. So if you take a curl of it, right, you remember that the omega is the curl of velocity. So we get equation Laplace omega equal to 0. Or you can take a diff of it. That would give you Laplace pressure equal to 0. So apparently, we now need to look for some part of a velocity which is related to pressure. Because, of course, we have this uniform solution. It satisfies the equation. It corresponds to pressure constant. Grad pressure is 0. But it doesn't satisfy boundary conditions. So now we are looking for an inhomogeneous solution which would have its pressure non-trivial, changing as a function of coordinates, and related to it part of the velocity. So again, pressure is a scalar, and how you relate, and it's a linear problem. So apparently it's the same. Pressure is u grad 1 over r. And it means that it's 1 over r squared. It's a dipole field, right? So if you plug it here, then this is 1 over r squared, this is 1 over r cubed, which tells you immediately that the inhomogeneous part of velocity is 1 over r. Good. And now I won't write this formula. This is Stokes PhD. So your velocity has a part which is 1 over r. It has another part which is 1 over r cubed. It is this potential flow. Together with two different constants, you can satisfy two boundary conditions. Everyone is happy. And then Stokes, somewhat later, already at his 30s, asked what would be a solution in 2 dimensions. You know, diffusion is always interested in 2 dimensions. And so you immediately recognize.
This one corresponds to what phi?
There is no phi, apparently. This is already non-potential part. It corresponds omega, which is also 1 over r squared, so it has vorticity. So you have potential part, which is homogeneous solution, and 1 over r, which is totally, what describes the diffusion of vorticity from your body. Because apparently no slip produces this type of a profile, which is a vorticity, right? But then Stokes hit a disaster. He said, look, this is a solution in 3 dimensions. But in 2 dimensions, all these things that you do, that would give you 1 over r, and that would give you log. It's interesting when you read a great man making wrong state. I mean, there is still, we have this 5 volume of Stokes, and it's a physical pleasure to read it. And then you see how a great man make mistake. It's also interesting. It's very interesting, not only how they do right statement. So when Stokes thought about it, of course, he physically thought that there is a cylinder. So you move a cylinder through a fluid. And after a while, he convinced himself that what actually happens, more and more and more fluid is involved into motion. At any finite time, it's in a finite distance. But that's what physically happens, right? And it was another great scientist, Rayleigh, who convinced him that it's not true. That, the argument of Rayleigh was that this solution, which you find out of this approximation, could not be true everywhere. Its validity is restricted in space. And the argument was very simple. So let's say we consider it in the reference frame of our body. So we have fluid moving with u like everywhere, and we impose a perturbation. This would be describing a perturbation to it, right? And then if you now look at this equation, you would see this as u dx, and this is 1 over r, which would be u 1 over r squared. But if you look here, you would have 1 over r cubed, because it's 1 over r twice differentiated. Okay? So what Rayleigh noticed and wrote to Stokes a private letter about it is that your solution could not be true at arbitrary distances. And this is in any dimension, apparently. Okay? So then you may ask what would be the distance at which you this solution stop working. And this distance apparently is nu over u. So when these 2 terms would be comparable, if you start from a small Reynolds number, this is a such distance. And essentially, the statement that Reynolds number is small, in other ways, you can say that the size of your body is much larger than the size of your, which we now call boundary layer. Okay? So that's essentially the idea. So now we have honestly understand how these 2 things talk to each other. So we say, okay, so when we have our body of the size r, there is a boundary layer of the size rb, and the Stokes solution with 1 over r decrease in 3D or with logarithmic increase in 2D would be working here. And outside, we will get approximation asymptotically approaching this potential solution where nonlinear inertia term would be dominating. Then you can do a beautiful theory matching the solution over there and the solution over here. And everything works perfect. You can do, this is called Asine approximation. You can compute correction to the force which act on a body, because in this case, it's easy to compute the force which act on a body. It's determined, first of all, by a pressure gradient, because pressure is now asymmetric. It's different here, and plus you also have a viscous stress tensor. They all proportional to the rho nu. And for a sphere, Stokes computed, and Asine computed a correction which is small Reynolds number correction. Okay. Everyone was happy. And then you start to think, okay, so this is a small Reynolds number. How we get into this, which is a large Reynolds number, and zero force? Well, zero force seems like nu goes to 0, then your force goes to 0. But this is 1 over nu, incidentally. This is, right? So when nu goes to 0, but you say, okay, it does not work when nu goes to 0. It's only small Reynolds number correction. So the question is, what happens when your viscosity goes to 0? Your Reynolds number increases, and you shrink your boundary layer to a size which is much less. So essentially, Reynolds number, it's a ratio between the size of the boundary layer and the size of the body. So the question was, as we shrink the boundary layer more and more, will it be smoothly going from one limit to another? Because what we have viscous solution inside the boundary layer, potential ideal solution outside. Okay, so that's for a physicist to imagine that something would happen like it's a finite parameter in the equation, right? You can write equation, just make everything dimensionless. This is 1 over a. Okay, so you have a parameter here, right? But we do know that birds fly, right? even before we had our planes flying, birds do fly. And they do fly with a constant speed, without acceleration. They could fly differently, but definitely. So this is something is wrong here, right? Totally. Not like a little bit. This picture is totally wrong. So something must happen. You want to comment on something?
You should say fish, not bird, because this is water. It's compressible liquid.
Look, when, depending on what kind of a bird you are, but you can fly with a speed much less than 320 meters per second, which you will still pretty much incompressible air. 1/20 of speed of sound is practically incompressible. Okay, so what actually happened? Like Feynman said, that all 19th century people were solving the equation of dry water, obtaining beautiful solution, matching all this. They've realized that it's a singular perturbation theory because it's a factor which is a small factor in front of a highest derivative. So you really, when you want to match what is over there and over here, you need to use very accurate mathematics. There's no relation to anything in the real world. And then an engineer came, which after it was made the professor of mathematics in Göttingen. There was a very dramatic transition of an engineer who was made professor of mathematics in Göttingen, Ludwig Prandtl, who realized what actually happening. And this is a very dramatic and interesting phenomenon. For if you imagine that this is a cylinder, that would be Reynolds number 4. If a sphere, I guess it's around 5. So at Reynolds number of order unity, not 100 and not 1/10, happens the following thing. So Prandtl said, let us consider the motion when it's really very large Reynolds number, very small velocity. And let's imagine what happens when our ideal flow comes from here. It was this understanding that something must be dramatically different before the body and after it. Because if you look at small Stokes, small Reynolds approximation, is just a diffusion of vorticity. Now, if you add to it transfer, you would understand that something, that your body must produce vorticity, and then inertia must somehow sweep it back. So Prandtl suggested to look at this flow which does not know that there would be a small viscous boundary layer over here, and something will be producing vorticity. And just look at this trajectory which passes close to a stagnation point here. At stagnation point, velocity is 0. Nearby, velocity is pretty small, which means that the pressure is high. So here, pressure is high. what happens to this fluid particle? Then it would go over here, and it would have maximum velocity over here. You need to go around the body, right? So here the pressure would be low, because we have this pressure and v squared somewhere, yeah. Okay. So now it's normal, it's absolutely clear that if you have a pressure high behind you, you're a fluid particle, right? So this high pressure behind you pushes you, and this is a low pressure, so pressure gradient drives you and accelerates you. Good. Then you need to repeat it, but other way around. So here again, you have a symmetric stagnation point. And at this stagnation point, again, pressure is high. So now what this particle does, it tries to go against the pressure gradient, right? What happens that in a totally ideal fluid, of course, it's a solution, right? So you can look at it and you see that this is, but now you have a little bit of viscosity. But this little bit of viscosity works all the way, which means it's a little bit less velocity here than you would have in a flow. It's pretty straightforward to show that the pressure distribution is practically the same, because you're interested in this pressure gradient, and viscous boundary layer seen in this direction does not change it. So now as you continue, you lose more and more of your velocity because of this friction near the solid body. So at some point, you just cannot overcome this. It's like you are running, like going like this, and you cannot get all the way up here. So what would happen is that at some point, the fluid particle here meets a gradient which is opposite, and it cannot overcome it. So it will be deviated away. And so, of course, because it's incompressible fluid, apparently the flow would be like this over here. So you would create a vortex. So you change topology at this. Okay? And this would go away. And this is phenomena which is called separation. And he made it on this talk on engineering congress in 1905. And great mathematician of Göttingen and all over Germany, they've heard about it and they've read it, and they were so impressed that they immediately understood that the new mathematics would go out of it. It was very, very hand-waving argument, engineering type. And yet, and they immediately invited him to go, and they created an experimental laboratory, which still exists at Göttingen, where he continued his study, etc. So, and this is a ray of order 4, okay? And of course, it's symmetric. And now you understand that, of course, in principle, you have this solution in which you would have a small boundary layer and a ideal fluid outside. Such solution exists. You may ask how it could be that the same equation at the same Reynolds number, let's say this is, it exists for Reynolds equal to 4 and for any other Reynolds number. Mathematicians still working. It's a very complicated thing to prove uniqueness of solution for this equation. But I think that for physicists, it's kind of, I would hardly to believe that for all factors here finite and a smooth solution and the same boundary condition, you would have two different solutions of this equation. I don't think so. The trick is that there are different boundary conditions. This is a solution with a boundary condition on a sphere exactly the same as boundary condition over here. No slip, no zero normal velocity, but it's different condition at infinity. Over here and over here. Here, in the ideal fluid, everything goes to infinity velocity as 1 over r cubed and its derivative. Now here, again, outside of a wake, everything is ideal, right? So ideal flow means that it did not pass through the boundary layer where you generate vorticity. And from here you come and you have zero vorticity, your potential. So if you come far away from the body, then you expect it to be in the same potential flow. Could we now say that at least in this direction, and in this direction, when you go to infinity, v will be 1 over r cubed? What's the idea? Wrong. Even that wrong. It's much more dramatic than you would. In all direction, it is wrong now. And that's what's really why this work of Prandtl was such a dramatic thing. So to understand this, you need, again, to be a little bit more like engineer. So let's return back to the force and act. What would actually will be the force acting on a body? And if Reynolds number go into infinity, then we may say that whatever viscous stresses exist on the surface, we can kind of neglect them, right? And Stokes tells us that the viscous force, where is the Stokes formula? Yeah, sorry, it was over here. That the viscous force will turn into 0. And so the question was, is there any force which we can say what we expect to be force when viscosity is negligible? And we know the answer for over 300 years from Newton. Newton said, yeah, of course, the force must be something which would be a typical pressure acting on your body times a typical area of your body. Or in other terms, Newton said, I mean, just look, you have a momentum rho u, and u is the rate with which this momentum is impacted to a fluid. So if you push a body with the momentum rho u, and every unit of time you pass distance u, then times r squared, it would give you a volume into which you impact this momentum. This is a true answer. Yeah, in a sense, of course, not 3 over 8. Yeah, this is a great irony of it. Well, of course, there is some kind of mathematics which is behind it. But still, we know the answer. This is a true answer. This is some factor which is not 6 pi. It depends on the shape of the body. And for sphere, it's some idiotic number which nobody were able to compute, which tells you the following thing, that if you plug this c, which is a dimension, it's called drag coefficient, right, as a function of Reynolds number, then at small r you are like Stokes tells you, and then you eventually expect it to come into some constant, not to 0, right? But now, if you really have a force, a drag, we aren't talking about lift yet. If you have a drag which is independent on viscosity, you can just compute it by a very simple argument which tells you take a surface very far from the body and compute a momentum flux through it. And yeah, we know what is momentum flux, right? It's so if this is y, x, and this would be z, so you need to integrate over this area at, let's say, x naught. So you need to just compute integral, which would be here pressure. You see, that's a momentum flux. We derive it on the first lecture, right? Just inertia, you know, pressure is an exchange rate of momentum between particles. Now you take pressure, which is P naught plus P prime. You take V, which is U plus V, and you assume that this is a small correction. Then you have constant, which of course gives you 0. Then you have here U squared term, which gives you 0. Then you have linear term, which would essentially will be a closed integral of the area times V, and this is just of df, and this is equal to 0. And then you neglect term which is Vi, Vk, assuming that this is small, because you are far away from the body, and even in the wake, you assume that the the velocity is small. We don't know yet how small it is, whether it's 1 over r, 1 over r squared, 1 over r cubed, but it's small, so we neglect it quadratically. And so what we linearly obtain is an integral over x minus integral over x naught of the quantity which is p prime plus rho u v. Okay, let's write v prime. So this is also correction, and you integrate dy dz. Now, it's pretty clear that if you streamline on which you live goes outside of the wake, you have Bernoulli's theorem, and Bernoulli's theorem tells you that p plus rho u plus v squared must be equal to p naught plus rho u squared. It's a Bernoulli's theorem, which tells you, if you look from here, that p prime plus rho u v prime equal to 0 outside of the wake. So you immediately recognize that your answer is, this is force, drag force, and this is the integral of a wake area. And then you can show that you can neglect the pressure against, for the reason that pressure does not change much across the lines, and what you get is the following thing: rho u integral v prime dy dz. It's actually integral over the area of the wake. Okay, this is force. Right? This could be in any position, right? I could just move it, and move it. Okay. What it tells me, and what is this over here? It's a deficit. It's a flux of velocity perturbation. It's a difference between flow without a body, which would be just uniform, and flow with a body, which produces a little deficit of a fluid coming through this area, and it is independent on the distance. I really want it to sink in. So just the fact that it is an empirical fact, which mathematicians proving, I mean, better and better, and showing that you actually, in the limit of infinite Reynolds number of zero viscosity, can have a non-zero force. It will be, as we discuss on next lecture about turbulence, it will be a non-zero rate of dissipation. But the moment you assume that there is a finite force at this limit, that's it. The answer is that this deficit of a fluid through the wake does not depend on the distance. What it tells me, because the fluid is still incompressible, that the integral outside of the wake must exactly compensate it. But the area over here grows like r squared, which tells me that this is 1 over r squared. Let's breathe a little bit and then say what exactly we just established. It's a charge flow. As if you had a source of a fluid, it's actually sink. But the source of a fluid is your wake. So you have a wake which essentially make it less going there. So you need to get something in, like as if it is a sink. So it's instead of dipole, it's a charge. Okay? So I really want you to see how non-trivial is this anomaly. But by anomaly, I mean nu goes to 0. Nu viscosity is a factor which breaks time reversibility, right? It changes the symmetrical property of my equation. It goes to 0. And even in this limit, when it goes to 0, it happens to give us the flow which is everywhere different from what we would guess. This flow is a solution. It's the same Reynolds number, it is a solution. We never could realize it, because the moment you take a body, you start accelerating it and then bring it to a constant velocity, and then you'll be moving and moving and moving it, it will be leaving behind a wake. It would never get into this solution. Even though it's a solution, it's a finite Reynolds number, it's a proper solution. Okay? So this is really a very dramatic consequence of how a world with a little bit of viscosity, of a friction, of a momentum diffusion, is totally different from the world with no friction or viscosity whatsoever. Okay? And this is, I think, is not only oldest in physics, but also one of the most non-trivial, right? That it's really to get its understanding how it's going on. Okay, and so now let's, is it clear? I mean, I really want here to take a deep breath, ask questions. How clear is this?
Transition. There is no phase transition. All the way to one limit to another.
It is a phase transition, and now I'll show it. So what I tell you, how solution, how flow looks like at very large Reynolds number. Now I want to describe you how you actually get there. So let's start from a sphere at a very, very small Reynolds number and see what kind of flow transformation we would undergo. Because
first a question. So you're saying that there is a phase transition. Phase transition corresponds to Reynolds number equal infinity. So we are never in the other phase. Right?
No. Okay. You ask question.
That's what you are saying.
No. First of all, there is no phase transition in any sense in which we had it before, in which you can have an order parameter which is identically zero on one side, and then it's getting non-zero either by jump or by anything else. You can, it's a topological transition if you want, but let's just go step.
But we are always in one phase. There is other phase not away. Right?
You mean that I have two solutions of the same equation with different boundary condition. So any engineer tell you, oh, you change boundary condition, you get different solution, right? If you somehow would be able to realize this boundary condition, this boundary condition, you would get this solution. Just we don't know how to realize it, right? So that's all, right?
It can be unstable, etc.
That's a separate thing, but this is still a solution of Navier-Stokes equation. So what's actually going on? And it's really interesting, and unfortunately it will be now more or less empirical, because not that many things that we're really able to derive. For example, I don't know, Landau tried, and I don't know, lesser people like me, just derive this angle. Or for, I don't know, for different things. But what's actually going on? Let's start now from really something that we do understand very well. Reynolds number, much less than unity, Stokes flow. And let's look at it not as engineer, but as physicist, and ask what symmetries are here. And then as we move and increase Reynolds number, exactly your question, what actually will be changing? First of all, there is up-down symmetry, discrete symmetry, it's here. Second, there is continuous symmetry times translation, it's steady solution. Is there a left-right symmetry? No, it's only approximate. Left-right is O of Re. So it's a little bit different here than here. A little bit, O of Re. But there is no such exact symmetry at, however, small but finite Reynolds number. Okay, good. Now, Re 4.5, what do we have? We have a very tiny opening here, but then it grows. A wake is something. So what? It's still up-down. It's still time translational. No exact symmetry is broken. What changed? Topology. There is closed line appears, and there is boundary condition at infinity appears. You want to call it phase transition, you don't want to call it phase transition, that's what happens. At this Reynolds now at 4, yeah? You go out of it, your flow change from this to this. On any finite distances, it's still very close to it, but it's slowly widening, the wake opening, okay? Then what? And when you get to a higher Reynolds number, guess what? What would you expect to happen with this solution? We still did not break any symmetry, but they will be broken at some point, right? We know what happens when you drive a car. There's no such symmetric wake, okay? What actually happens is the story which von Karman very funnily gives in his memoir. He was a PhD student in Prahn's lab. Von Karman was one of these Hungarians, Martians. And there was a guy who was measuring a resistance of a cylinder. There was a cylinder, there was a basin, the fluid flow, and they measured it as a function of Reynolds number. At some point, they found oscillations. And there was absolutely clear to everyone involved, starting from Prahn and ending with the assistant, that this is because the cylinder was imperfect. So there were kind of vortices, kind of, you know, here and here. And so they polished the cylinder every day. And Karman was kind of a little bit lazy, so he came usually later in the morning and says, how? They say, it still oscillates and will polish it even more. And at some point, Karman gave it a little thought, and he realized what actually happened. What actually happened is that around this number, you really break symmetries. True, the symmetry which were exact, you break. You simultaneously break two symmetries. You break time invariance. Your flow is starting to get non-stationary, and you break up and down symmetry simultaneously. And as it often happens in physics, when you break two symmetries simultaneously, you replace it with one combined symmetry. So you see what actually going on is the following thing. That when you increase the flow, these vortices, the flow is getting too fast for these vortices to really establish some area circulate. And they start get detached. But they detached by breaking a symmetry up and down, because they detach one by one. This is why your resistance oscillates. So it's on one vortex, then another vortex. So what's going on is what we now call Karman vortex street. So there will be which means that you replace continuous time translation and discrete up and down symmetry by a symmetry which is translation in time by a period of vortex shading and up and down symmetry. Okay, so this is two symmetries is replaced by one another, and returning back to the problem with which we started all this business, namely a bubble in champagne or in Coca-Cola. If this bubble is large enough, you can find out that it goes up in a zigzag. Why? Just a bubble. It goes up, but it makes zigzag because of this. You see the relation? It moves, and then it sheds vortex from this side. At this point, it turns this way. Then it sheds vortex from this side. At this point, it turns this way. Shedding vortices, and that's what airplane does. Insects are fantastic in this thing. When they hover, that's what they do. They shed vortices from here, and they shed them exactly in phase, so that it gives them boost. And that's, you know, a dragonfly. And now we visualized it, so we really can see how exactly and beautifully they can shed vortices from their ends. Okay, good. What we expected even higher Reynolds number. Let me go to the other side. When Reynolds number is getting larger, we expect that the symmetry will be still further broken. And at some point, we find out empirically that on this curve, something like this happens. It's around 10 to 5. The guy, yes?
Two symmetries will break and one combined symmetry will come.
Yeah, the combined symmetry which exists in this situation is the following symmetry. Change up and down and translate in time by a 1/2 period of shading vortex. You see? Because in half period, what you will see this picture, which means it up-down, right? Because first this vortex shed, but then it goes and the vortex here appears, then it goes and the vortex here appears. That's what it kind of oscillates, okay? It does this, exactly like you say, it does this. And that's why a bubble, you need kind of a little bit larger, but you can see it. Beer does it pretty well. I mean, the zigzag motion. And of course, you can go to YouTube and find the
vortex shedding. Article.
U divided by R times unbelievably complicated geometrical factor, which for sphere is now pretty well known, but it changes with the Reynolds number. The geometry of your vortex changes, of course, but time is R divided by U. That's.
Was there a relation with the shape of the surface, like how polished it was?
Of course, yeah. Just look, people spend trillions designing streamlined bodies which shed as little as possible, because essentially your drag is this width. Why you make a wing, right, of an aeroplane? It creates a wake which is very, very thin. It's a very little drag, right? And then the vortices over there is pretty elongated. What, by the way, I tried sometime and failed miserably. I tried to describe vortices in this when they are very elongated. You may still try to describe it as close to a unidirectional flow, and then a little, because you do need vorticity, you do need closed streamline, but it will be very much like this. It's singular perturbation theory, and it's doable probably, but I did not do it.
Any connection to this condition?
Yeah, in a sense, everything here is about how life would be beautiful without vortices, like in superconductor. And then some boundaries or singularities or whatever, which produce vortices, and vortices come out of a boundary of your region and go inside and make it turbulent and create all the type of problems. Most evident difference, of course, is that our vortices aren't quantized. But on the other hand, I believe there is some deep connection. It is mostly related to the fact that, after all, it does not matter whether vortices are quantized. Vorticity is something which changes your flow. I told you in the first lecture that when Euler first wrote Euler equation and he immediately sees that it has a beautiful potential solution, he was ecstatic. And in a couple of weeks, maybe even less, he realizes there is vorticity, and he was devastated. He immediately understood that this is a problem for centuries to solve, which is we are 270 years after Euler derived his equation. Okay, so let me finish this story with this drop. So this is drop at pretty high Reynolds number. The guy who discovered is Eiffel. You know who Eiffel was? Absolutely, of course, because how you would measure it at a really large, you need a tower. Why we build towers? To draw bodies. Well, Russians draw humans, well, did sometimes, no. But Eiffel did a lot of experiments, not only with his Eiffel Tower, of course, but like Galileo, but with really measurements, measuring how fast, essentially measuring drag. Because when you drop from a very big height, eventually it comes to a constant velocity, right? And so you can, Prandtl explained it. Eiffel observed that Prandtl actually found an explanation. Prandtl was a genius. It's a drag crisis. Yes? Coriolis effect would matter too. It would be a little bit aside, yeah. Which means that if you really want to drop it on somebody's head, you need to do corrections on Coriolis force.
Do you see any relation between drag and Coriolis?
No, they're perpendicular to each other. It's just couple. You ask something? Nope. Okay, so this is our first window, and that will be last 2 lectures. By the way, it will be November 22 and 29. The last lecture, there will be turbulence. But this is the first window into turbulence. It's called drag crisis. Eiffel discovered it, and then, because in the laboratory it was still not very easy to do, but then people eventually reproduced it in the laboratory. What happened is that Prandtl realized that, of course, your wake is something which is a transversal kind of a gradient of velocity. So velocity is here a little bit higher than here. That's precisely this v correction. Incidentally, you can show that here is indeed v1 over r in the wake, but it's small, which means that but it's still a transversal gradient. Transversal gradient always make eventually your flow unstable. The moment that you kind of, maybe the simplest argument, if you have something like, well, in the reference frame, you would have flow like this, which you may say that this is like vorticity over here, right? And if you have a set of vortices of the same sign, it's always unstable with respect to shifting one vortex a little bit like this. Then the other 2 vortexes would continue increase this perturbation. So what Prandtl realized, that at this precisely Reynolds number 10 to 5, that the boundary layer itself were getting unstable and getting turbulent. How turbulization of a boundary layer could decrease drag acting on a body? Okay, so this is the observation. We at Reynolds 10 to 5 for a sphere. By the way, for soccer ball, good soccer players can use it very, very beautifully. It's a speed like 25, 27 meters per second. So sometimes when you shoot over a goalkeeper, it moves like this. And if you add Magnus force to it, it just could work beautifully. But so at the same Reynolds number, we see that boundary layer is getting turbulent. I mean, really, you see something like this. Not, and of course, and the wake is also getting turbulent. And the drop in the drag. And Prandtl explained it. His explanation was as following. The drag essentially is a width of the wake. Your u is given, right? But essentially your deficit, because you remember this formula about relating, where is this? Was somewhere here, to this integral of vx dy dz rho u. That's my force. So it's an integral over the wake area. And what Prandtl realized is, as the boundary layer is getting turbulent, it's essentially effectively getting more thick and kind of more inertial, and the wake is getting more thin. So what happens at 10 to 5, your wake shrinks in this neck, and has the most thin part. And then it now continues to grow, but for people like us who are trying to do turbulence and all this, what we now get is that we get into this asymptotics. Here is infinite Reynolds number, all our turbulence, it will be next lecture about it. But in terms of a drag acting on a body, we come from below, not from above. Again, there are different geometries, and wind could be different, and a needle could be even more different. But this is essentially the picture. So what we now have as a result of it, let me reiterate, and on this I finish. So we solve the equation at 2 limits, and we have dimensionless parameters, called control parameters in this case. And then we found out that as we scan this, that this is not going into that. That there is something, some transition, which is, I would not call it phase transition because it's different. Right? It's different, and incidentally, it kind of was understood before all this beautiful, and long before physicists started to focus on symmetries. Not long before, actually, few decades before. And then Kolmogorov realized the dissipative anomaly 10 years before Schwinger, which means that this already were pretty close. But the general idea is that the flow with a little viscosity, it's different in the whole space. Not only behind the body, but also across and in front. If you really wait long enough, and it's an incompressible flow, that your flow is different everywhere. You have 1 over r squared charge flow. It's a little bit of a flow coming towards the body, right? And as a result of it, we have a dramatic consequence that our force does not go to 0, it goes to a constant. And in the next lecture, we'll realize that it means that we are burning, literally, at every cubic centimeter of a fluid, we are burning energy which is independent asymptotically on the viscosity, and that will bring us to turbulence and its cascade, etc. That will be 22nd of November, I'll remind you, and then 29th of November. Questions? That's easy way out of questions. Okay. Okay, so if there are no questions, then see you.